So the last section of this module 1 is, of course, examples. So we're going to go through some examples to justify and apply the learned series in previous slides to see how they really work. I call example 1, 2 as warm-up examples. And to the rest of examples, I suggest all of you to pause the video and try yourself to see what kind of trouble you could have and confirm your solutions with the key. Okay, let's start with example 1 here. It's about a very practical battery charging issue. Feel free to pause the video to read through the problem, and here I'm just go ahead to present the solution. My solution will be presented under a dog cam. Hopefully it's clear and organized enough. If any problem, just bring it up in the office hour or via email. Anyway, example 1. What we are seeing here is actually, it is mentioning 1000 milliampere hour. I believe the first thing we have to figure out is milliampere hour is talking about what? Remember in the video I ever mentioned the unit of a quantity is not only telling you the magnitude or size, but also telling you what this quantity is. So here is a very typical example for that. And so milliampere hour is the unit of what? Without knowing this, we can't proceed. Okay, and the answer is the unit of charge. How could that be? It's because of this equation we learned. Okay, the current is equals to the rate of change of charge. So you can tell the charge could be equal to the current times a certain amount of time. Therefore, the charge unit could be the current unit, which is ampere, times the time unit, which is second. So obviously here is using milliampere and hour, so they're pretty much making sense. So 1000 milliampere hour is talking about the charge of the battery. So with this amount of current, how much time means nothing but dt requires to charge this amount of charge. How much charge we need to charge? Well, it's a little bit twisting, but hopefully you know what I mean. So fully charged means 1000 milliampere hour. Empty is meaning 0 milliampere hour. So the difference between them is the dq, is the total amount of charge you need to charge. The total amount of charge divided by total amount of time spent is equals to the current. And now the current is given as 250 milliampere. The total amount of charge you need to charge is 1000. So denominator dt is the time spent equals to this, the ratio between dq and I. Turned out to be 4 hours. Is the time you have to use to charge fully. After fully charged, of course, immediately the battery has 1000 milliampere hour charge stored. No problem for that. It's not necessary, however, if you want, you can do a conversion from this unit to SI. And so 1000 milliampere hour equals to 1 ampere hour, and also equals to pretty much 3600 ampere second, right? And ampere second is SI for charge. In other words, 1 ampere second is equal to 1 coulomb. So end up with 3600 coulomb. Okay, be feeling much better about this coulomb unit, I believe. And the question B is asking for how much charge left. So following the same idea, so fully charged 1000 minus 200 milliampere current times this amount of hour, and then end up with 200 milliampere hour charge left, and convert it to column, which is 720 column charge left. And to example 2, we have up to 5 elements in the circuit and looking for the power of 5. And also looking for the voltage across it. How to do this problem. Again, feel free to pause the video. And so obviously, by reading the problem, you need to first understand this is a example for so-called power conservation. Now, what does it mean by power conservation? It means the total power in the network, in a complete network, should be 0. How to think about this? You can think in this way, that the power provided by something equals to the power consumed by others, right? So if you count in the providing and consuming into the sign of the power, then the summation of them total is equals to 0. For this particular example, we have 5 elements, so sum their power together, we should end up with 0. And by reading the problem further, we should come up with these 4 results. Okay? Because the description in the example is not telling you the sign of the power. So we translate that description into the sign. We should have P1 is positive 40, P2 is negative 50, and so on, so forth. So sum them up, we can come up with power of number 5 is positive 20 watt. Positive power means what? Absorbing, or say consuming. However, be careful, the problem we're asking is tricky, I have to admit. However, it's helping you understand the concept better. The question is asking how much power the element 5 supplying, not consuming. So how should we answer this? We should say 5 is supplying negative 20 watt, which is equivalent to consuming positive 20 watt. And also looking for the voltage across the 5. What we should notice is how to find the voltage. The power 20 watt positive is equals to V5 times I5. Right? I5 is given as negative 2 ampere, and also be careful the passive convention. The negative 2 ampere as it is entering into the positive polarity of the V5. Therefore, we just directly apply V5 times this negative 2 ampere. It equals to positive 20. Therefore, V5 equals negative 10. Now let's take a look at the example 3. Find the power by each element in the circuit A through D. So here we are seeing A through C, and the D circuit is on next page. So let's go over the circuit A here. We are seeing 3 elements along one single loop. Okay? And along this loop, you have one unique current, Ix, 4 ampere. So we can tell easily that each element here has the same current of 4 ampere. Let's see how to find the power for each one of them. So I'm using different subscript to differentiate different elements. For example, the power of 24 volts voltage source has power of P sub 24 volt, and it equals to the product between the current through it and the voltage across it. The current through this 24 volts voltage source is 4 ampere, as we said. However, you see this 4 ampere is entering the negative polarity of the voltage source. Doesn't match the passive sign convention. So here we can either flip the voltage polarity or flip the current direction. If we are flip the current direction, and then resulted current becomes negative 4 ampere, and the current entering the positive polarity of the source. And that way we can use negative 4 times the voltage 24 volts, ending up with a negative 96 watts. Negative power means supplying or delivering power. Second, the element 1 has voltage of 8 volts, and a 4 ampere current is entering the positive polarity of it, so matching the passive sign convention. We just directly apply 4 ampere times 8 volt, positive 32 watt absorbing power, or say consuming power. The third one, the dependent source. This dependent source is a voltage source due to the sign here, a polarity labeled. And this voltage source voltage value is depending on Ix, which is a current. So this dependent source is a current dependent voltage source with voltage value of 4 times 4, 16 volts. And the current through it is 4 ampere as well, entering the positive polarity in this loop. So we are using directly this 4 ampere times the voltage, 16 volts, ending up with 64 watt positive, absorbing the power. And if you verify these results by power conservation theorem, you will see sum them up, ending up with 0 watt. Perfect sense. Obviously, now you want to pause the video and try circuit B and C. And be careful in circuit B, the Ix is given as 2 ampere. And you have a current dependent current source in the middle. And apply the same idea we learned, you should end up with this solution. Okay. And to circuit C, you have a current dependent current source as well, with voltage labeled here. The trick of the circuit C is that Ix here is not given. However, and what can you do is by applying a power conservation theorem, you sum up all of the power together. It should be equal to 0. And each one of the power is in terms of Ix. So you can find Ix at the end and substitute this resolved Ix value back to each power and then to obtain the specified numbers. Okay, so please try them over and come back to check the solution yourself. And in the circuit D, last one, we basically follow the same idea to find each element's power by voltage times current and trying to match the passive sign convention. And the trick of this circuit is that we don't know the current of element 3, which is I naught. It's something we don't know again. But what we can do is similar to circuit C. We apply the power conservation theorem and sum up all of the power together, and is equals to 0, from where you can find out the I naught value and substitute this value back to the P3. We can find the specified watts value. So just be careful also the dependent source. So this is a current dependent voltage source here. So exercise them yourself and then come back to check the solution and bring up the questions and concerns in the office hour. Now let's see next example 4. Find the equivalent resistance at the terminal A and B in the circuits A through C. So this is pretty much looking for the total resistance. How to solve such kind of a problem? Remember two things. Number one, there are only 4 types of connections you need to identify. And they are series, parallel, delta, or Y. Okay, only 4 you need to identify successfully as the basis of finding the equivalent total resistance. Second thing you need to do is following the circuit order. Begin with the end of the circuit and moving towards the beginning of it, part by part. Okay, following these 2 ideas, let's try circuit A here. Okay. We're beginning from the end of circuit. Actually, we're considering the terminal A and B as the beginning of the circuit. So the end of it is pretty much this part, from where we can see a clear series connection between 3K and 6K. Combining these 2, and then we see a clear parallel between 18K and this combined 3 and 6K. After that, we see this entire thing is series connected with 6 and 10K. And then pretty much we are done with finding the total resistance RAB. And here is the solution here. 3, 6 series parallel with 18K. Well, of course, here I've been using this parallel double bars as the representation of parallel. Let me know if you don't follow the meaning of it. Okay, so parallel will follow the parallel equation. You can calculate 1 over the sum of reciprocal of each one. Okay, and then series with 6K and 10K. The correct result is 22 kilo. And to go back to the circuit B here, again, we follow the order of from the end of the circuit, beginning of the circuit, and the end of circuit is obviously here. Another clear series connection between 1K and 2K. After this, you can see a clear parallel between this 6K and this 1K, 2K. After combining these 2 parts, you see another series with 10K. And so on and so forth, move towards the beginning of the circuit. And at last step, you can imagine that actually series with this 2K up here. Right? So try yourself to see if you can get the correct result. The last circuit C here, you're seeing something different. You're seeing a delta connection, right, among these 3. Or you're seeing another delta connection among these 3. They're overlapping by this 18 kilo ohm, therefore you don't need to do 2 conversion from delta to Y. You want to do only 1 conversion from delta to Y, either upper one here or lower one here. Only 1. The goal of converting delta to Y is that the result could have clear series or parallel. Since now, without doing that conversion, you can't see any clear series connection nor parallel connection. Okay, so be careful. All right, so try yourself and then come back for the solution. And here you're seeing the solution for B, bunch of series and parallel. Okay, so let me know if you have any questions or any part I need to teach more. And to circuit C, I'm converting the upper delta to Y following the conversion equation provided in the previous slide. So after that, I end up with 3 resistors here. So from here, you can see clear series connection between this one and this one. Also, between this one and this one. After combine them respectively, you see these 2 are actually parallel. And then from there, you basically know what to do to the next. Okay. The correct answer for this total resistance is 34 kilo. Right, next example, number 5. Well, you can notice that the difficulty level is actually increased gradually. And let's see, find different things in different circuits. First, circuit A, looking for the I naught, which is the current through 3K here. Okay. How to find it? First of all, remember there's always more than one ways to solve the same circuit. And here, based on what we have just learned, I'm planning to use the current divider. The reason is I'm seeing one independent current source here, which is pretty much providing the total current to the entire circuit, or say network. So if I can somehow combining the rest of circuit into two parallel branches between the single pair node, I can apply the current divider to find the current anywhere. So based on this thought, I start to work towards that way. So I'm seeing, first of all, 3K and the 6K here are clearly parallel connected. So if I combine them together and then series with 4K up here, it becomes one single branch, which is parallel with this 12K branch. So clearly a basic current divider. Of course, you're seeing two elements. By that, I'm saying pretty much one branch parallel with another branch. Only two branches, two elements, share the total 9 milliampere current. So by doing this, I'm able to find this branch current, because the ultimate goal is to find the I naught here. So find the current through 12K is meaningless. So find this branch current, which is also the current through 4K. This is a very important thing you need to realize. So the current flow through 4K is in which direction is another thing you need to figure out. So if you think of this circuit, so basically 4K current and 12K current total is equal to 9 milliampere going downwards. So from here, the current of this 9 milliampere is towards right. Therefore, the current of 4K is upward. The current of 12K is towards right as well. Does it make sense? So the sum of these two current equals to this current. And this is how I judge the current direction of 4K. Due to that, you can see the 4K current is actually the sum of the current through 3K and 6K, which is the second current divider here. And the 3K current, for the same reason, is upward. So is the current direction of 6K. So by applying the second current divider, you can find I naught. This is pretty much I naught. However, it has the opposite current direction compared to the given one, label one, which is downward. So what we need to do is this current is actually not I naught, but negative I naught. Right? So by two current divider and a little combination, you can do the job. So here is the solution specifically. So first of all, as I said, looking for the current through 4K. We know the current through 4K is supposed to be upward. However, if you're looking for the downward current, is actually equals to negative total current times the ratio. In the numerator is the other branch resistance, which is 12K. Denominator is the sum of 12K and the 4K branch containing the parallel between 3K and 6K here. So the current through 4K downwards is -6 milliampere. And using this current to do second current divider shared by 6K and 3K, since they're in parallel, you got I naught, -4 milliampere. Now let's see circuit B here. So based on circuit 1 analysis, we should be able to open our mind to an idea that as long as we are seeing only one independent source, we might want to think of voltage or current divider as one of the solutions, at least. Here, be careful. It must be one independent source. No more than that. If you have two independent sources or even more, no, you can't do that directly. If you have one independent source and you have one or more dependent sources, you can't do that either. Okay, it must be one single independent source, and then you might think of current or voltage dividers. Okay, so this is also the case for circuit B here. Also C and D. So pretty much example 5 is all about the voltage or current divider. Okay, so going back to circuit B here, one independent voltage source. So we are thinking of voltage divider. So how to do that? Again, no matter is current or voltage divider, we need to think of two elements. Okay, total voltage here shared by two elements. If there are more than two elements in the circuit, you need to combine them becoming two, and then you apply the voltage divider equation. Okay, that's a very, very important thing. So to do that, obviously we can clearly see a series connection between these two. After that, this guy is parallel with 30. Okay. And then this total thing gonna share the 12 volts as total with this 20 kilo ohm. Okay. So pretty much this guy is series connected with this guy in the single loop circuits, so that we are able to apply voltage divider between these two. Okay. After that, you got the voltage. That voltage is the voltage cross here and here, right? Which is not equal to V naught, the one we are looking for. Okay, be very careful. And clearly, you're seeing second voltage divider. The total voltage here is shared between 20 kilo and 40 kilo here. So by this second voltage divider, you should be able to find the voltage cross 20 kilo ohm, which is our true V naught as the final result. If all of these saying makes sense, please take a look at the solution here, from where you can see two voltage dividers. Total 12 shared by 20K, and the combination of those three. And you're looking for the combination voltage, which is also the voltage cross 30 kilo. And by applying the second voltage divider, as we said, you're looking for the voltage cross the 20K as the final result V naught. So the correct final result is 2 volts V naught. Similarly in circuit C here, clearly one independent voltage source. We are thinking of voltage divider again. This is actually easier than circuit B. However, the trick is it is looking for the Vs, which is the total voltage. How could we do that? We can find the voltage cross 60K, which is the voltage here, from here to here, between these two nodes. So pretty much if you combine 6K and the 120K, you can see their combination is series with this 20K here, becoming a single loop circuit here for you to write voltage divider equation. And then the voltage here could be found by that, and it equals to the voltage cross 60K, and 60K voltage is equals to the current times resistance based on the Ohm's law. So following this idea, so 6K ohm voltage is equals to resistance times the current equals to 6 volts. And by applying voltage divider, it is also equals to total voltage times a ratio. And the numerator is the combination between 60 and 120. Denominator is sum of 20 and this combo. Is equals to the 6 volts we obtained here, from which we can find Vs value. So the correct answer is 9 volts for Vs. The last one, single independent current source. So we are thinking of current divider. And we again need to combine the rest of the circuit into two parallel elements, branches, to share this total IS. So similar to circuit C idea, we don't know the total current IS. However, we can find one branch current, which is here. So this current following this given voltage with its polarity is going downwards current 3 volts divided by 30 kilo ohm. After knowing this current, we can combine 90 kilo ohm and 30 kilo ohm together. Becomes one branch parallel with another one. So two branches, two elements share the total IS as this. So the 30 kilo ohm resistance current is equals to the voltage divided by resistance, 0.1 milliampere. Be careful, it's downwards. And then by one current divider here, we can find this current is also equals to total current times the ratio. In the numerator is the other branch, which is 60K. Denominator is sum of 60K and this branch, which is series connection between 90 and 30K. Equals to 0.1 milliampere, which we obtained from up here. From this equation, we can find IS equals to 0.3 milliampere. But here, pay enough attention on this current direction. We call it downwards. The reason is going back to the circuit, because the positive is here, negative is here. So you use this voltage divided by 30 kilo ohm, give you the current from the positive higher potential point towards the lower potential point, negative. Actually, same attention should be paid in circuit C, in where the given current 0.1 milliampere through 60K ohm is downwards current, introducing the voltage having the voltage polarity positive up here, negative down here. So imagine, what if the current direction given is another way around, upward? How to solve this problem? So now we finished all of the content of Module 1, including basic concepts, connections, relations, and followed by several examples. Please review the knowledge and especially spend enough time on practicing the examples yourself. Bring up all of your questions in office hour. Fully utilize it. Thank you. See you in next module.